Hello and welcome to biochemistry tutorial number 1. Today we'll be talking about enzyme inhibitors. Inhibitors are molecules that prevent enzymes from converting substrates into products. There are two main types. Irreversible inhibitors are molecules that bind covalently or via very strong ionic interactions to the enzymes. They are very tightly bound and thus they do not dissociate easily. Reversible inhibitors are molecules that bind via weaker non-covalent interactions such as hydrogen bonding, hydrophobic interactions, or van der Waals forces to the enzyme. They dissociate more easily because their interactions are not as strong. And there are three main types of reversible inhibitors that we will talk about. So an example of an irreversible inhibitor is a transition state analog. So enzymes favor the transition state over the substrate. So transition state analogs are stable compounds that mimic the transition state, and they bind to the enzyme more readily than the substrate because the enzyme favors the transition state more than the substrate. And with that, we're ready to talk about the three main types of reversible inhibitors. There are three main types of reversible inhibitors: competitive, uncompetitive, and non-competitive, also called mixed. So first we have the competitive inhibitor, and the competitive inhibitor directly competes with the substrate to bind to the active site. So here we have both the inhibitor and the substrate, and they can both bind to the active site of the enzyme. So if we look at the reaction that's going on here, we have the enzyme and the substrate and the inhibitor. So the inhibitor can bind to the enzyme to form the enzyme inhibitor complex, and the substrate can also bind to the enzyme and form the enzyme substrate complex. Before I talk more about the effects of inhibitors, I need to discuss two plots that are going to be very useful. So first, we have the Michaelis-Menten plot. On the x-axis, we have the concentration of substrate, and on the y-axis, we have the velocity of the reaction. And this is a measure of how much substrate is converted to product per time. So the value that the graph approaches is called Vmax, and this is the max velocity. At 1/2 Vmax, here we go, we have 1/2 Vmax. The concentration of substrate at that point is called Km. Km is also called the Michaelis-Menten constant. A high Km means the substrate has a low binding affinity for the enzyme. And finally, another plot that we use is the Lineweaver-Burke plot. The x-axis is 1 over concentration of substrate, and the y-axis is 1 over velocity. The y-intercept is 1 over Vmax, and the x-intercept is negative 1 over Km. The slope of the Lineweaver-Burke plot is Km over Vmax. And the Lineweaver-Burke plot is useful because it is a linear line. So for each inhibitor, we'll discuss the effects on the Michaelis-Menten plot and the Lineweaver-Burke plot. First, for the Michaelis-Menten plot, Km will increase and Vmax will not change. So for the Lineweaver-Burke plot, the x-intercept, -1 over km, will get closer to the origin since km increased. The y-intercept, or 1 over Vmax, will not change because Vmax did not change. And the slope, km over Vmax, will increase because km increased. So let me write that down. M, which is a symbol for slope, increased. Okay, so let's draw 1/2 Vmax. So remember, Vmax did not change, but km increased. So if we were to draw the line for the inhibitor, let me label this as plus I, we should see that km plus I is greater than km minus I. So for the Lineweaver-Burke plot, remember, -1 over km, or the x-intercept, got closer to the origin. Here's the origin. The y-intercept did not change, and the slope increased. So here is what the line would look like with the inhibitor. So next we have the uncompetitive inhibitor. So this inhibitor only binds to the enzyme substrate complex, or ES, and it binds to a site different than the active site. So you can see here the inhibitor binds to this site and the substrate still binds to the active site. And from the equation, the inhibitor only interacts with ES. So for the uncompetitive inhibitor, Km will decrease and Vmax will decrease as well. And this is for the Michaelis-Menten plot. For the Lineweaver-Burke plot, the x-intercept will get further from the origin since Km decreased. The y-intercept will increase because Vmax decreased. Remember, the y-intercept is 1 over Vmax. And the slope will remain unchanged since both variables decreased. So M, no change. So let's draw out the effects. So here's the new Vmax. Remember, Vmax decreased plus I, because this is for the inhibitor. And here's the new 1/2 Vmax. And you can clearly see Km plus I is less than Km minus I. So for the Lineweaver-Burke plot, we have the x-intercept getting further away from the origin and the y-intercept increasing. So here's plus I, but notice how the slope is left unchanged. We just have a parallel, the line just seems to be shifted parallel upward. So finally, we have a non-competitive or a mixed inhibitor, and this inhibitor may bind either to the active site or the enzyme substrate complex. So the reason why it's called mixed inhibition is that this part, the inhibitor binding to the enzyme, is the competitive part, and remember, the inhibitor can also bind to the enzyme substrate complex, or ES, and this is the uncompetitive part. So it's a mix between competitive and uncompetitive inhibition. So for non-competitive inhibitors, Km can either stay the same, increase, or decrease. It's usually drawn as staying the same, and Vmax will decrease. So for the Lineweaver-Burke plot, the x-intercept, it depends on what happened to Km, whether it stayed the same, increased, or decreased. The y-intercept will increase because Vmax decreased, and the slope will usually increase because Vmax decreased. Alright, so let's draw out the effects on the two plots. So here's the new Vmax. It decreased. Vmax. And here's the new 1/2 Vmax. So in this case, Km decreased. And for the Lineweaver-Burke plot, we have that the y-intercept definitely increased, and here we'll just draw the Km value staying the same, and in this case the slope increased.